Okay, everyone, thanks for coming to what is probably going to be the final anomalology talk of this semester, and we'll start up again in the fall, unless there's any surprise encore talks in the middle of the summer. But yeah, we're really excited to have Rajath, who is currently a postdoc at ICTP, give us our final talk of the year on non-anomalous, non-invertible symmetries from SymTFTs. So take it away when you're ready.
Okay, thank you. Thank you for the opportunity to give this talk. So I'll talk about non-nodal symmetries, particularly in 1+1D, and how we can kind of extract non-anomalous, non-invertible symmetries, starting from a 3D TQFT, which is studied a lot in recent years, called SymTFTs. And this is based on this paper which came out a few weeks back with Pavel. So, of course, let me start by saying that there are, of course, a lot of work on this topic. So if I miss your reference, please don't be offended. So let me start with a quick motivation. So we have come to realize that in QFTs, topological operators play a special role in the sense that they implement these generalized symmetries. And in a general QFT, the topological operators have a very rich structure. Like conformal bootstrap, you can try to do a topological bootstrap where you try to impose this condition that if you have a topological point operator, you really want it to be independent of the position of the operator. If you have a topological line, you really want it to be independent of the shape of the line, things like that. So you impose these topological bootstrap conditions in some sense and kind of trying to decipher what is the algebraic structure behind it. So usually you have some kind of categorical nature to these operators. Usually you have a layer of topological operators of various kinds. In a d-dimensional QFT, you have a layer of operators of various codimensions. So higher category, which also has a layered structure, comes out as a natural setting to describe such operators. Now, in a generic QFT, these topological operators can be quite rich and quite wild. Even if we restrict ourselves to a finite set of such operators, they can be quite rich. But there are, of course, special QFTs, which we call TQFTs, where all operators are topological by definition. So everything that you see are topological operators. And in such QFTs, the topological operators are more constrained. For example, in 2+1D, if you have topological lines which can braid with each other, a generic QFT can have a general set of line operators which may or may not braid non-trivially with each other. But in a TQFT, we want the braiding to be modular. So there's a modularity condition on the topological line operators in a TQFT. So this modularity condition often allows us to classify TQFTs in some sense of the word classify, which is quite hard to do in general, in a generic QFT. So the SymTFT, how that becomes important is that a SymTFT is a TQFT which can capture many topological properties of a QFT. So now we have a d-dimensional QFT, and the d-dimensional QFT has many topological operators in it. And a SymTFT is a d+1 dimensional TQFT. So a simpler setting in a sense, at the expense of going one higher dimension, which captures a lot of properties of the symmetries of the d-dimensional QFT. So it is a method in which you can use TQFTs and properties of TQFTs to study symmetries and topological aspects of a generic QFT. So that is how SymTFTs are interesting. And of course, there are very important works and much more exploring SymTFTs and how they're important for this process. So a SymTFT, which I will denote by the Z of C, anticipating some structure, has two different boundaries. Usually you have some boundary BC, which is a gap boundary. So you only have topological degrees of freedom on that boundary. And you have another boundary BQFT, which is a generic, which I've labeled here QFT because this boundary is often very complicated. It depends on what is the d-dimensional QFT you have. and as complicated as the QFT. But on the other side, you have a gap boundary which has topological degrees of freedom, and this is the setting that you're interested in, where you have a gap boundary on one side and generically a gapless boundary on the other side, and you use this bulk d plus one dimensional TQFT. So the bulk is also topological to study topological aspects of this QFT. So I will say much more about this and in concrete cases, but this talk is about how to determine non-anomalous symmetries. Oh, I completely erased something. How to determine non-anomalous symmetries in the d-dimensional QFT, starting from the SymTFT. So that is one of the goals of the talk. So any questions on the motivation at this point? Okay. Okay, so the plan is I will start with invertible symmetries in 1 plus 1D, because invertible symmetries and their SymTFTs will basically highlight the main method of computing these non-anomalous symmetries from the SymTFT. So I will talk about invertible symmetries and their SymTFT. So these are three-dimensional TQFTs which capture invertible symmetries in 1 plus 1D QFTs. Then I will describe the S3 symmetry case, because the S3 symmetry is a non-abelian case and the simplest case in which you can actually analyze everything explicitly, and you can already see the general story there. Then I will describe non-vertical symmetries in 1 plus 1D, look at their SymTFTs, and find how to describe a generic method on how to find non-anomalous symmetries from such general SymTFTs. And then I will describe some applications. So this is the plan. So let me start with a quick review of symmetries in 1 plus 1D. So we have in general a generic QFT Q in 1 plus 1D, and we assume that the QFT has some symmetry G. So now it's an invertible symmetry. There is some group G. G is non-abelian in general, and every group element labels some line operator. So there's these yellow lines are some topological line operators which are labeled by group elements, and these are the lines which implement the symmetry, which act on the local operators, for example, of the QFT, and implement the symmetry G. Now, when you consider junctions of line operators like this, if you have a configuration of line operators like this, they often differ from a configuration like this. So there's usually a type of crossing relation between these two types of configuration of topological lines, and they differ by some cocycle, some phase. And this cocycle is the anomaly of the symmetry. And the reason why this has the interpretation of the anomaly can be understood by looking at the gauging process of G. So this square should be thought of as torus. So you identify the sides of the torus of the square. So if you gauge the G symmetry, it's essentially putting the topological lines across the cycles of the torus. So you have the torus, you put the lines across the cycles and across both cycles of the torus. And when you have crossings like this, you have to resolve it into some trivalent junctions. So this kind of crossing can be resolved either to these kind of configurations or to these kind of configurations. But you don't want the gauging, the resulting QFT to depend on the type of network you have, network of these topological lines you have. So if you want to gauge G, this omega better be trivial, because otherwise there is no consistent way of resolving these junctions into trivalent junctions. So this is how, in one way, you can understand why omega signals anomalies. If this omega is non-trivial, if you try to do the gauging procedure, it will inevitably depend on this kind of data, but you don't want that. So this is kind of a setting that we will start with. Now, given a G, we could have some subgroups which are non-anomalous. So G itself will have some non-trivial anomaly in general, and we will not be able to gauge G, but there may be some subgroup K which we can gauge. So how do we determine that? It means that this omega, which is some cocycle, so omega was an element of this cohomology group, which depends on G. If we restrict that to K, it should be trivial in the cohomology of K, for K. So the anomaly is non-trivial in the full group, but it restricts to something trivial in the subgroup. But there are multiple ways by what you mean by this restriction. So this omega restricted to K should be trivial in cohomology, So what it means is that omega restricted to k is some d psi for some 2 cochain. So there is some function on the group, and d psi is this omega. And whenever you have a solution, you can just multiply the psi with some alpha in this second cohomology group, and you get another trivialization. So this omega being trivial, a choice of trivialization involves choosing a psi, but then once you choose a psi, there is another choice, other choices labeled by this alpha, which we often call the discrete torsion. So we have the discrete torsion, and it will play an important role in our story. And the possible gaugings. So if we have a symmetry G with anomaly omega, the different gaugings that you can do, you can just write them down. It's a finite group. You have a finite number of subgroups. So a finite number of subgroups which satisfy this condition. So such subgroups, along with a choice of trivialization, is a set of all possible gaugings you can do. So this is the data you have. So let us look at an example. Straight away, let us look at the S3 case. So S3 is generated by R and S. I will choose the labels R and S. This is just, of course, you're all familiar with S3, but I will just use this notation so that we carry along that notation till almost till the end of the talk. So we have R comma S, where R is order 3 and S is order 2, and we have these relations which tell us what the group is. And what in this case, we will assume that there is no anomaly. The omega is trivial, just for simplicity. So that means that any subgroup you can gauge. So the possible gaugings is just given by all possible subgroups you have. S3, there's a Z3 subgroup generated by this R. There are 3 Z2 subgroups generated by S, SR, and SR squared. And there is the trivial subgroup. So we have all of these possible gaugings. Now, this was a purely 1 plus 1D discussion. We had a symmetry, we have an anomaly, we have some non-anomalous subgroups. In this case, we looked at S3 and found the sub.
We lost the speaker temporarily. Rajath, we temporarily lost you, but I think you had just finished telling us that there were basically 6 subgroups, and you were about to introduce the SymTFT.
Okay, sorry, yeah.
So we're good now.
Yeah, so we have the SymTFT, and in this slide, we are looking at the SymTFT for this particular invertible symmetry G with anomaly omega. And this is the diagram-ridden theory based on with gauge group G and the action determined by omega. So this I will just write it as dwg omega. So it is described by all of this data. And as I said earlier, there is a gap boundary which corresponds to this symmetry G and anomaly omega. This is a completely gapped boundary. And there's another boundary which is BQ, which is about the QFT, so which contains the QFT data. So this is the SymTFT. Now, the different gaugings, possible gaugings that we discussed in the previous slide, they can be understood using this SymTFT picture, and we would like to make that explicit. Okay, so before going into the S3 example in particular, let me describe the data that describes gap boundaries of SymTFTs. So a gap boundary of a SymTFT is almost completely determined by the set of lines which can end on the gap boundary. So you have to choose. So the question is, what are the lines which can end on the gap boundary? And in general, you have this line L in the bulk, which is a sum of simple lines. So X are some simple line operators. Simple means line operators which cannot be written as a sum of other lines. So you have a sum of simple lines, and these are the lines which can end on the gap boundary. These lines must be bosons because these lines become trivial on the boundary, and the trivial line has trivial spin. And there is a maximality condition, this Lagrangian condition, saying that the dimension of L should be the same as the size of the group. So here the dimension of L is defined as this sum here. So given this Lagrangian algebra object, you take the quantum dimension of X and you sum over the quantum dimensions with these integer coefficients. And that is the dimension of L. And we require that to be equal to the size of the group G that we started with. So this is a Lagrangian algebra. And these conditions can be understood as by thinking of gauging L. So if we have some SymTFT, a gap boundary is an interface between the SymTFT and the trivial TQFT. And the interface is created by starting with the SymTFT, gauging a maximal set of one-form symmetry given by this L. And that gives us the trivial UFT. That's how you get this gap interface. So that is also why you need the spin to be 1, because it's telling you that this L can be gauged. We want it to be non-anomalous. But this only almost completely determines the gap boundary. This is not enough to determine the gap boundary. The remaining data that you need comes from this name that L is in Lagrangian algebra. So L is not just an object. L is the sum of X. And in this definition, L is just a line operator in the category, the SymTFT. But there's an algebra structure on L. And what does that mean? It means that if you have two lines X and Y, which ending on this gap boundary, you can either end them one after the other like this, or you can fuse X and Y first and then end the resulting line on the gap boundary. And there is a map between these processes, ending X and Y directly or fusing them and then ending the result of the fusion. And these are some complex numbers which has to satisfy certain consistency conditions. I will not go into the consistency conditions because we will not use this M directly in the examples that we have, but these can be found. And these conditions, along with these complex numbers, means that L is a Lagrangian algebra. This is the definition of a Lagrangian algebra. And this is the data that determines the gap boundary. So if you want to look at the set of gap boundaries of the SymTFT, you have to supply this data. What are all possible L which satisfy these conditions? Any questions on this? Now, let us go back to the S3. So we have the conjugacy class, we have the set of subgroup of elements which commute with G, the centralizer of G, and you look at all the irreps of that centralizer and the data, the Wilson, the magnetic, electric, and ionic lines of the Dirac theory are labeled like this. So let us look at the Dirac theory for S3 explicitly and see what is the data. So in this case, we have the trivial conjugacy class, the conjugacy class S, the conjugacy class labeled by R, and we have these centralizers. For the trivial conjugacy class, of course, is S3. For S, it is this particular centralizer for the representative S. And for the representative R of this conjugacy class, the centralizer is this. And we can look at the irreps. S3 has 3 irreps. The trivial one, the one-dimensional one, and the two-dimensional one. This is a Z2 subgroup, so it has only 2 irreps, all one-dimensional. And this is a Z3 subgroup, and it has 3 irreps, all one-dimensional. So we can use this data and write down all the line operators we have. So what is a line operator? We have E1, E pi 1, E pi 2. These are the electrically charged ones because they have trivial conjugacy class dependence. And these are the quantum dimensions of these line operators. So this is invertible, this is invertible, this is non-invertible line. And there is S1, S sigma, which are also some line operators which have quantum dimension 3. And the quantum dimension is given by the size of the conjugacy class multiplied by the dimension of the representation. That's what I have written down here. So that is the quantum dimension. And you can see that these ones in orange, they're all bosons. So they're all bosonic line operators. S sigma is a fermionic line operator. This you can compute by the action of sigma on S. So that's the definition of the spin. So you will find that there's a fermion. These are all bosons. And we have a few more lines depending on R. We have R1R, R omega, and R omega square, which are all quantum dimension 2 line operators, which are all non-invertible, and only this one is a boson. Now, I've highlighted the bosons because, as we discussed, a Lagrangian algebra is, to find Lagrangian algebras, we have to first identify the bosons in the theory. So we found this boson and these bosons here. So any Lagrangian algebra you have is a combination of these bosons. So what are the Lagrangian algebras that we have in this case? We have 4 Lagrangian algebras. One of the Lagrangian algebras is this canonical Lagrangian algebra, which means that this is just the Wilson lines put together, E1, E pi 1, and 2 times E pi 2. So you often have this 2 because this is like the quantum dimension of this line. Here you have 1 because these lines have quantum dimension 1. So this is a canonical Lagrangian algebra that you have. In a generic SymTFT, you can always identify this. There is 3 other Lagrangian algebras. One is E1, E pi 2, and S1. These are all bosons. You can check from the table above. E1, E pi 1, and 2 times R pi R1R, and E1, S1, and R1. So you have these completely a Lagrangian algebra which depends only on the flux, the conjugacy classes. So we have these 4 Lagrangian algebras, and as I said, actually one has to solve for these multiplications that I mentioned here to actually show that these are Lagrangian algebras, to completely fix everything. You can check that these conditions are all satisfied, like the dimension of any Lagrangian algebra that I mentioned are all equal to the size of the group, which is 6. All of them are bosons, but one has to also find these. So I have borrowed the result. I mean, I'm sure this is in other papers also. For example, I have borrowed this set of Lagrangian algebras from this paper, where they have also written down the complex numbers, these multiplications as well. So we have looked at the S3 SymTFT for S3, and we have also looked at all the Lagrangian algebras for that SymTFT. Now the question is, how do you extract the possible gaugings from the Lagrangian algebra? So this is where the bulk to boundary map comes into picture. So you have the SymTFT, which is this 3-dimensional TQFT, and you have this gap boundary corresponding to the S3 symmetry. So among the 4 Lagrangian algebras that you have, we choose the canonical Lagrangian algebra. We will always choose the canonical Lagrangian algebra here as the gap boundary which has the symmetry that we are looking for. So we started with S3 symmetry, and we looked at the SymTFT for S3, and we will choose this canonical Lagrangian algebra as the gap boundary. So that is why I have BL1 here. I have the bulk diagram theory, and what the process that we are interested in is fusing a bulk line on the boundary. So you have a bulk line, a generic bulk line, G pi G. You cannot generically end this line on the boundary. If this line belongs to L1, you can end it by definition of the gap boundary. But if this line is not in L1, you cannot end it. And there's a tail, there's an orange tail. So I will call this tail as F acting on G pi G. So what is this F? F is a map from the SymTFT, the 3-dimensional TQFT, to the boundary symmetry S3. So this is how you should think about it. From the TQFT to the boundary lines. So these lines, the orange lines on the boundary, form the group S3. And what is this map? This map is basically just taking out the conjugacy class data. So you apply this F to this, you basically get the sum of elements in this conjugacy class as the outcome, multiplied by some dimension factor, which if pi g is higher dimensional, there will be some dimension, non-trivial dimension factor here. But in general, it will be just taking out the conjugacy class and writing all the elements in it explicitly. So let us apply this F map to the 4 Lagrangian algebras that we had before. So remember that we had these 4 Lagrangian algebras here. We apply F to these Lagrangian algebras. So this should be thought about as ending the Lagrangian algebra object on the canonical gap boundary. So what happens if you end L1 on the canonical gap boundary, L1, every line can end on the L1 gap boundary because you are ending L1 on L1. So every time you end, you just get a copy of the trivial line in S3. So let us look back at L1. What was L1? L1 was E1, E pi 1, E pi 2. If you apply F to E1, you get E. If you apply F to E pi 1, you get E. If you apply F to 2 copies of this, you get 4 copies of E because you have 2 here and this representation is 2-dimensional. So that is why you get 6 copies of E as the outcome when you apply F. And these numbers are actually important. That's why I'm writing down all 6 copies of E, even though F acting on each of them is just some copies of E. It is important to keep track of this number 6, as we will see. F acting on L2 now will be something non-trivial because L2 is a Lagrangian algebra, but it is not a Lagrangian algebra corresponding to this boundary. So all lines in L2 cannot end on this boundary. So when you apply F using this formula, you will find that this is this sum, which you can write it as E plus S, E plus SR, E plus SR squared. Similarly, you do for L3 and L4. So what do we see? For L1, you just get 6 copies of E. So this is like 6 copies of the trivial subgroup that we know we can gauge. If you apply F to L2, you get E plus S, E plus SR, and E plus SR square, which give you the 3 Z2 subgroup of S3. If you apply to L3, you get E plus R square, E plus R square. So 2 copies of this Z3 subgroup. And if you apply F to L4, you get the full group. So if you forget about these multiplicities that you see here, like 2 copies of this algebra, 6 copies of this subgroup, then you find that you have got all possible gaugeable subgroups in S3 from the Lagrangian algebra. So this is how you get all possible gaugings. Now note that you had 1, 2, 3, 4, 5, 6 subgroups. These are the 6 set of gaugings you can have. But the SymTFT has only 4 Lagrangian algebras. So when you apply F, you get these outcomes, but these 3 are grouped together. And there's a physical meaning to the fact that these 3 are grouped together. And the physical meaning is that if you gauge the Z2 subgroup of S3 generated by S, it is the same as gauging the subgroup generated by SR. It doesn't matter which Z2 subgroup you gauge, you will get the same theory after gauging. So what this means is that these Z2 gaugings are physically equivalent. This only happens in a non-abelian group because these Z2 subgroups are related by conjugation. So whenever you have subgroups related by conjugation, you can check that these 3 Z2 subgroups are related by conjugation by some other element. Then any subgroup which is related by conjugation, when you gauge, they give you the same QFT. So they are physically equivalent gaugings. So what this tells you is that when you get gaugeable subgroups from Lagrangian algebras of the SymTFT, the outcome automatically tells you which gaugings are physically equivalent. And the Lagrangian algebras knows only about physically inequivalent gaugings. So from a given Lagrangian algebra, the outcome is all the gaugings which are physically equivalent comes out. And a simple example of that is this S3 outcome. So this is actually an important example. So please, if there are confusions regarding this, let me know. And this
I think it's,
yeah.
Sorry. I was just going to say, so just to be like, when you're talking about gaugings in 2D, do you prefer thinking about them in terms of like, algebras in the term, not Lagrangian algebras, but, like whatever, the ones with all the adjectives, special, Frobenius, blah, blah, blah. Or, I mean, really, you're labeling it in terms of module categories, I guess, of FECG. Okay. Is there an obvious map between the algebras you gauge and the module categories?
Yeah. So I will get to the algebra language because I was in the invertible case. I was not introducing the algebra language yet. I will discuss the algebra in the non-invertible case and tell you how you can get those from this. And indeed, the module categories for those algebras will play an important role in finding what these multiplicities mean. You get 2 copies of this, 6 copies of this. This multiplicity has to do with the module structure.
Okay, perfect. Thanks.
Okay. So let me go to non-invertible symmetries. Again, this will be a brief introduction to non-invertible, what is the data that describes non-invertible symmetries. So we have again some line operators, which I will label A, B, C. And now you have generically a non-group like fusion rules for them, some ring-like type fusion rule. And again, you have some associator, this omega, which was there in the group-like case, becomes certain matrices now, which relates again these two diagrams. And of course, there's a lot more indices on these objects. I'm not going into the details about what are all possible fusion spaces and what are all the indices to be added. But these are some F, which are often called F matrices or F symbols, which essentially captures the anomaly again of the category. But I'll be more precise about what anomaly means soon. So at this point, you can think of it as some isomorphisms which relates this diagram and this diagram. Now, by gauging, you are interested in, similar to the S3 case, when you had S3, the full S3 might have some anomaly, but you can still ask about gauging a subgroup of S3 if that subgroup is non-anomalous. Similarly, when you have a full category C, which is fusion category, because you have the fusion rules and you have the associators, you can think about gauging a sub-symmetry in a way. What do I mean? I would like to gauge some line operator A, which is a sum of simple lines. So A, B, C denote simple lines. Is A lines on the manifold you have. And you have, in order to do that, you have to choose mu in such a way.
Yeah.
But okay, so hopefully it works. Can you hear me now properly?
Yes.
Okay.
Thank you.
No problem.
Hopefully it helps. Yeah.
So we require this anomaly vanishing condition. So with this choice of mu at these junctions, you have to make sure that this condition 1 is satisfied. So A is some line operator. You can choose A to be any line operator, but you have to choose some mu which satisfies this condition, and such a mu may not exist. So this is how you say that A is anomalous, which means that an arbitrarily chosen A cannot be gauged because there is no mu which satisfies this condition in general. But for some A, you may have a mu. So if A is anomalous, if mu satisfying this constraint 1 exists. So that is what I will mean by an A being non-anomalous. Also, if A is non-anomalous, that means if there exists a mu which satisfies that condition, that actually there may be multiple mu which satisfies that condition 1. So I will call that a choice of a generalized discrete torsion, because in the case of a group-like symmetry, this mu, a choice of mu, is precisely the discrete torsion that we discussed. In this case, it's a generalized discrete torsion. In fact, this algebra for gauging, you need to choose a lot more data on this algebra. But this is a minimal data, this is a necessary condition if this algebra A contains only one copy of the identity line. So here it is a generic sum of line operators. From now, I will assume that there is only one copy of the identity line in this algebra. If you assume that, then this actually is sufficient, because the other structures that you actually need, like there's a Frobenius structure, there's a symmetric property of the algebra, all of that comes along once you know that a mu exists. You can determine it uniquely. So I will only focus on this mu, because that is what the basic data that tells you whether there's an anomaly or not. So this is the analog of a non-anomalous subgroup in the non-invertible case.
Do you mind telling us more about what exactly mu is? Is it a vector space or?
Yeah. So if you have so this is actually an element of this home. So there's a home space. So you take A times A, whatever A is, you can choose A times A using this fusion rule. And from that, you find common elements between A times A and A. And you can write this home space explicitly in some basis. And mu is some complex numbers. This is like the M that we described for the Lagrangian algebra, similar to that.
And then what does the consistency condition say?
Yeah, so there is, if you can write this down explicitly, there will be an expression involving, once you choose all the basis, a set of basis elements, you can find some expression like mu times the F matrix is some combination of F. I don't remember how many copies of F appear actually. There'll be some expression involving mu and F explicitly, which you have to solve. So there will be some polynomial constraints involving the F matrices, which are here, which you already know because you assume that you know the full category. And you have to find some solution to such polynomial conditions. So these conditions are given in several papers. In my paper, I have given a simplified version of this condition. I won't be looking more into it because we can kind of get this from the Lagrangian algebra data. I will discuss that later. Yeah, but you have to solve for certain polynomial equations.
Perfect. Thank you so much.
Okay, so let me look at the Fibonacci category. So let us jump into an example before we lose track. We have this category of line operators, the trivial line and this non-trivial line tau. Tau has a particular fusion rule. Tau times tau is 1 plus tau. And the simplest non-invertible symmetry you can imagine, because it's rank 2. And there are two symmetries you can gauge in this Fibonacci category. So you have to actually find the mu in this case, solve for the mu using the F symbols. But I'll just take the results from these papers and just tell you the answer that, of course, there is always the trivial algebra. You cannot gauge anything. And you also have this A2, another algebra, which is this 1 plus tau. 1 plus tau also happens to satisfy this condition 1. So there is some mu which satisfies condition 1 for 1 plus tau. So 1 plus tau is also something that can be gauged. But it's a genuinely non-invertible gauging because you have this tau appearing here, which is a non-invertible line operator. Okay. Now, given a general line operator, how do we know whether a mu exists or not? Of course, one way, as I said, is to look at the F matrices and solve the consistency conditions and check whether mu exists. Another way is to use the SymTFT, like in the case of the S3 discrete case theory. We start with S3, we use the bulk to boundary map to find what are all the things that we can gauge. Similarly, in this case, we can use the SymTFT, use the bulk to boundary map, and find all the algebras which we can gauge. So now it is slightly complicated. You have algebras coming in, but the method is exactly the same. Okay, so what is the SymTFT of a general fusion category? So a SymTFT of a general fusion category is C. I will denote it as Z of C. This is sometimes called the Drinfeld center of C. This is also sometimes called the Levin-Wen model because you can write down a state sum construction, and the state sum is quite useful to explicitly find the line operators in this SymTFT. The important part of the SymTFT that I would like to mention that is important for the discussion is that line operators in the SymTFT, the simple line operators in the SymTFT, has this kind of notation. You can write down all line operators in the SymTFT in this way: A, comma, EA. What is A? A is some object in the boundary category. So it's some line operator in the boundary category. EA is certain maps between A times B and B times A. So note that if you start with a generic fusion category, here is a generic fusion category. This category doesn't have a notion of braiding lines because you are in 2 dimensions. In fact, you can start with fusion categories which do not admit any braiding. So there is no braiding at all. But the 3D SymTFT is a TQFT where lines are living in 3 dimensions. So you should be able to braid those lines. So when you go from a boundary symmetry to a bulk TQFT, you should introduce a braiding by hand. And this EA, B are basically such braidings. They are not quite the full braidings. They are called half braidings. And this is basically a way of introducing a braiding between A and B. And these have to satisfy several consistency conditions. But what I would like to mention is that you can always write a line operator as this 2-component labeling. One is an object of C, other is some half braiding. This half braiding again will not play an important role in our discussion. So that's why I'm not going into details. The important thing that you should remember is that you can write it in this way. The lines, you can write it in this way. Okay, again, a gap boundary of a SymTFT has exactly the same description as we described in the S3 case. It is some line operator. Now I'm writing all lines in this A, EA fashion. And some line operator such that, again, it is Lagrangian, so it has this maximal size. But this maximal size is now defined according to these dimensions. Dimension of L is again the sum of quantum dimensions. Dimension of C is a sum of squares of quantum dimension. So there is this Lagrangian condition. All lines must again be bosons. But as I said, there is a multiplication on L which has to be solved explicitly. So there is this M, which is a multiplication on L, which we need to solve for. So that is another data which we need to, in general, find. So this is, again, the data that describes a gap boundary of a SymTFT for a generic non-invertible symmetry. Okay, so again, we have a bulk to boundary map. The bulk to boundary map is, again, looking at some line operator in the bulk and then fusing it on the boundary. But the boundary may not be the boundary which contains this as a Lagrangian algebra. So this is a generic line operator in the bulk. When you bring it to the boundary, you get some tail. And the tail is this yellow line, which is, I will again denote as F acting on this line. And this is the bulk to boundary map from the center to the boundary category. This is the boundary category here because I will choose this boundary to be that boundary whose line operators form C. Because we started with C, we found the SymTFT for C, and there's a canonical gap boundary on which the lines are C, using which we constructed the SymTFT. So that is this gap boundary. So the bulk to boundary map is a map from the center to the boundary. And what is this map? When it acts on this data, it just forgets about the half braidings. You just get A as the outcome. Quite simple. So this is called the forgetful functor, if you're familiar with the math literature. And it's called the forgetful functor precisely because it forgets about the half braidings. You just get A as the outcome. So any questions till now? Okay. So what is the claim? The claim is that
Actually, wait. Could I just ask? So you're basically saying, sorry, in the case of like abelian symmetries, I know that this bulk boundary, or sorry, that the half braiding map is basically the sort of it's like a change of basis, maybe I would say, between describe. I don't. Okay, let me see. Maybe could I ask? Could you explain the half braiding matrix again somehow? I'm trying to fit it into language I know, and the language I think of it is it's like a change of basis between describing boundary conditions by like in terms of the anyons that you condense versus in terms of like the algebra you gauge or something like that.
I mean, the way I understand the half braiding data is in the way that even though the boundary category doesn't have a braiding on it, once you have like, so if you have like A, EA here, and you have some boundary line operator B, sitting here. Okay, you have the bulk line A comma EA, and you bring it to the boundary, and similar to the forgetful functor, this becomes A here. But you can bring it also to the other side because you have a 3D space to move around in. So you can either bring it from this side or that side. So that means that there's some kind of commutation relation between A and B if you are allowed to take A and into the bulk and move around B. And these isomorphisms are things that capture that half braiding. They are half because you have to keep one on the boundary and the other one in the bulk. This is the way in which I understand it. In the case of discrete case theories, this is almost like the representations that you attach to the conjugacy clauses. But in general, yeah, I'm not sure if there is a nice way. Yeah, except for this diagram, I don't know. Yeah, a nice way to describe them.
I see. Yeah, I was thinking of it in a different way, which is that, if you imagine that you take the TFT on a solid cylinder,
Okay.
and the cylinder has finite length, so it's got some boundaries. That there's essentially two ways to describe the space of states at the boundary. You can either have a line run up vertically along the solid cylinder. I guess it would be helpful if I had my camera on, but you can have a line run up the solid cylinder, and then it like sort of punctures the boundary.
Okay.
Oh, that's amazing. Okay, you're live drawing. Yeah. And so there's boundary conditions. Essentially, a good basis of states at the boundary is labeled by sort of these configurations, if you will. And then there's another basis for this vector space where the lines are just literally at the boundary.
Like you mean like around here, or?
Yeah, yes, essentially, yeah. And then the half braiding matrix is kind of the quote unquote change of basis matrix between these two collections of states. So I was just trying to relate that to what you were describing. I mean, they must be equivalent, but I
see. Yeah. I think I vaguely remember something, but yeah, I this is probably right, but I have to think about it more. Yeah. I don't exactly remember how to relate it to half ratings directly, but yeah.
Okay, sorry for the interruption.
No problem, yeah.
Thank you.
Okay. So the main claim is that we just do the bulk to boundary map. So given some Lagrangian algebra in the bulk, you just apply F to it, the bulk to boundary map to it, and you get some sum of lines in the boundary. And this F applied to L is a non-anomalous line operator of the boundary category. This is the claim. This is what we did in the S3 case. And we can do this in the Fibonacci case to understand a bit more. Okay, let us go back to the Fibonacci case. So the Fibonacci category is actually, you can think of it as a modular tensor category because it admits a braiding and it admits a modular braiding, in fact. So the SymTFT of the Fibonacci category C is actually has a very nice form, which is C times C bar. So C bar is like a category whose you can think of as the braiding has been inverted. RXY becomes like RYX. So it's a product of Fibonacci and Fibonacci with the braiding inverse. So the line operators can be written in a very simple way in the SymTFT. If line operators in the Fibonacci, remember, where this 1 and tau. So the line operators in the SymTFT can be written as 1, 1, 1, tau, tau, 1, tau, tau. Now these have spins. These are the spins. 1, theta tau, which is this complex number. Again, theta tau, and 1. So we have these. We have two bosons here, and any Lagrangian algebra of the SymTFT Z of C must be made up of these bosons. So a Lagrangian algebra can be written in terms of these bosons. But before doing that, let me actually change the notation. As I said, the forgetful functor is easiest to describe when you write lines as objects, half braidings. And this is not that notation. This is a notation which comes naturally from C times C bar. We have to change our notation to a notation which is of the form A, EA. Again, we don't care about these EAs because they are completely forgotten about in the half-braiding map anyway. They are completely forgotten about in the forgetful functor anyway. But there is still a way of writing these lines as objects, half braidings, and that is given here. There's an isomorphism between C times C bar and the A, EA way of describing the differential center. We have to use that isomorphism to write this down. The trivial line is 1, E1. For E1 is some half braiding. 1, tau is tau, E tau for some half braiding. Tau, 1 is also tau, some new half braiding. Tau, tau is 1 plus tau and some half braiding. So this house maybe it's something weird because this is a simple line operator of the SymTFT, but 1 plus tau is not a simple line operator of the boundary, but this is allowed. And if you look carefully, the first component of this notation is just fusing these two. Whatever is here, you just fuse them and you get the first component. We can write down these half braidings explicitly in terms of the R matrix of Fibonacci. I will not do that here because we won't need it. Once we write the lines in this form, the Lagrangian algebra, there's only one Lagrangian algebra in the Fibonacci, and that is this 1, E1 and 1 plus tau, E 1 plus tau. That is the two bosons that we have. Now, we can see readily that if you apply F to L, you get 1 plus 1 plus tau, which can decompose into two algebras because you have two identities coming in. Remember that we are interested in algebras where only one identity show up. When you apply F, you get some algebra which has some lines, some multiples of 1 in it, but you want to decompose into some sub-algebras with each algebra having just one copy of the identity line. So in this case, you have 1 plus 1 plus tau, you decompose it, you get the algebra 1, and you get the algebra 1 plus tau. But remember, I told you that when you get multiple algebras, gauging them are physically equivalent. If you get multiple algebras from the same gap boundary. In this case, you get 1 and 1 plus tau from the same gap boundary. Therefore, 1 plus tau, gauging 1 plus tau, should be the same as gauging nothing. Which means that 1 plus tau gauging is actually a self-duality of the Fibonacci category. When you have a QFT with a Fibonacci symmetry, you gauge 1 plus tau, you go back to the same theory. This is like the Ising, where you gauge the fermionic Z2 and you get the you get the Z2 symmetry, of the Ising. And when you gauge it, you go back to Ising itself. This is the Fibonacci version of that. And you see that 1 plus tau must be a self-duality because 1 and 1 plus tau comes from the same Lagrangian algebra. So any questions on this example?
So could you use the same technology on Ising, since Ising is also braided, and so it's Schoenfeld center, like Z of Ising is Ising times Ising bar, or?
Right, yeah, we can use the same on Ising. So the Ising bulk SymTFT will have a Lagrangian algebra, which is like psi, psi plus sigma, sigma. There will be a canonical Lagrangian algebra for Ising. If you write it in this fashion, this object, half braiding, this is actually 1, E1 for some half braiding. Psi, psi will become 1, E1, 1, E1 prime for some new half braiding. And sigma, sigma will become 1 plus psi with some half braiding 1 plus psi. The way I'm writing down this is, remember that to go from this to this is just fusing these two, using the fusion rules of Ising. So 1, it gives 1, here psi gives 1, sigma times sigma gives 1 plus psi. Now if you apply F, you get 1 plus 1 plus 1 plus psi. That is how you know 1 plus psi is a self-duality, like gauging 1 plus psi is a self-duality.
I see. Thank you.
Okay. So yeah, I feel like I've used almost the whole hour. Let me kind of give you an idea about what is going on here. Like when you apply the F map, as you see in the Ising case, for example, it's a good example because if you apply F to these three lines, you get 1 plus 1 plus 1 plus psi. So you get two copies of the identity algebra and one copy of the 1 plus psi algebra. In this case, you get one copy of each algebra. But already in the S3 example, we saw that we get many copies of different algebras. So why do we get all these copies? What is the meaning of those copies? It has a very precise meaning, and that meaning is important because when you apply F to some arbitrary L, you wouldn't know how to decompose it into subalgebras. Like if you get some sum of things, how do you know how to decompose it? So knowing what this F of L means is important to decompose it into these individual algebras, which are all equivalent under gauging. So for that, I have to go back to the C-symmetric TQFTs. So let me be slightly quick here because of the time. So we can start with the SymTFT again, and we can choose two gap boundaries. BC is a gap boundary corresponding to the symmetry C, and BL is some other gap boundary given by Lagrangian algebra L. If you have two gap boundaries, this is a sandwich picture, right? You shrink it and you get some C-symmetric TQFT, which I will call TL, because L is important. The choice of gap boundary here determines which C-symmetric TQFT you're talking about. It always has a C-symmetry because you have fixed this boundary to be this BC. As you change L, you get different C-symmetric TQFTs. If you have a line operator which ends on both sides, when you shrink this picture, you get a topological local operator of the C-symmetric TQFT. This is how you get some data of the C-symmetric TQFT from the compactification of the sandwich picture. Some line which is ending on both sides gives you a local operator. If you have a line which ends on one side, and if you have a line which has a tail on the other side, when you shrink, you get a twisted sector local operator. It is a local operator. It's not really a local operator. It's a point operator which sits at the end of a line operator, which is clear from this picture. You shrink it, this line becomes this point, and this yellow line remains as a topological line of the TQFT, and that's how you get this twisted sector. Now we have to look at slightly different. We have to look at like something that you could call like the taco picture, like the sandwich, where you have a wedge of two gap boundaries of the SymTFT. Here it was not a wedge. Here you take a wedge of two gap boundaries. You again have this BC and BL, but you take this wedge. So you have to choose an interface between BC and BL. So you have to choose an interface between these two gap boundaries of the SymTFT, and you just collapse this wedge. What it gives you is a C-symmetric TQFT with a choice of a 1D gap boundary. So this interface between these two gap boundaries of the SymTFT becomes a 1D gap boundary of the C-symmetric TQFT. So this is how you get information about the gap boundaries of the C-symmetric TQFT starting from the SymTFT. You can also determine how lines act on gap boundaries. And if you have this X in the bulk, which is a bulk line operator, you end it on this BC boundary. But as I said, X may not be able to end. So you'll get a tail, which is this A. And you choose an A which doesn't change this gapped interface. That means if you act with A, if you try to fuse A on alpha, you get alpha itself. Or more precisely, there is a junction, consistent junction between A, alpha, and alpha. If you fold this picture, if you collapse this wedge, you will basically get A action on M alpha. M alpha is the 1D gap boundary corresponding to alpha. And this, after you collapse this picture, what this tells you is that A is a line operator which preserves this 1D gap boundary. So this picture is important. So any questions on this? So this is where you will see the modules coming in, because if you know the module category picture, the modules label gap boundaries of the TQFT, if you have a TQFT in the 1+1D case, and this is where the modules will come in. Okay, so let me just remind you certain results in category theory, that if you have a TQFT TL, and suppose ML is a set of gap boundaries of the TQFT. There's a finite number of simple gap boundaries Whereby simple, I mean the gap boundary does not host any non-trivial local operator. So the same definition of simple as for simple lines or simple surfaces. If ML is a set of gap boundaries, you can define AM for a chosen gap boundary M as a set of lines which can form a junction with that gap boundary. So if you have some, so I should have chosen here M. I don't have to discuss the alpha at this point. So if you choose a gap boundary M, you can look at the set of bulk lines which can form a junction on M. And this set of lines, you can write it down like this, where A appears in this, if A can form a junction here. This is an integer which tells you the dimension of the space of operators on this junction. So this is a line operator. The important thing that Ostrich showed when he introduced these module categories is that AM is a non-anomalous line operator. You can put an algebra structure on AM simply because this module exists. So these gap boundaries are modules, and simply because these gap boundaries are consistent by assumption, you can put some algebra structure on AM, which means that AM is a non-anomalous line operator. And this is the crucial part where we introduce the module category part and the algebra part. Given these boundaries, gap boundaries, you can construct these non-anomalous line operators. And these are the line operators that shows up in when you do the bulk to boundary map. What is the claim? When you do F, the forgetful map or the bulk to boundary map to a Lagrangian algebra, the sum that you get, the sum of algebras that you get is precisely these AM, which are the algebras that you get by looking at lines which can preserve a given gap boundary. So you have a sum of algebras for different M. For different gap boundaries, for each M, you have a AM. And you take a sum of all such algebras, you get F of F acting on L. So these AMs are the physically equivalent gaugings. Like in the Fibonacci case, we found 1 and 1 plus tau. Those two are algebras which come from certain modules, certain gap boundaries of the Fibonacci symmetric TQFT. So this is the structure of F of L, and this is how you can look at F of L and decompose it into a subalgebras and look at which gaugings are equivalent. Questions on this? Okay, so I don't know if I should, let me actually skip over the proof. The proof is not complicated. It is just using the fact that this diagram, when you shrink it, it gives you a twisted sector operator. And basically saying that once you do, if you have some A which appears in F of L, so A appearing in F of L means that when you end L on the gap boundary, you find A. In fact, there are NFLA, so this is an integer. There are these many ways of ending L and getting A. And what this tells you is that there are many log twisted sector operators that you get from this shrinking process. And the dimension of that twisted sector Hilbert space is actually given by this integer n. So whenever you apply F to L and you get some multiplicity here, that multiplicity has to do with the size of the Hilbert space of this twisted sector in the 1 plus 1D theory. So here, the 1 plus 1D theory I'm taking is as the TQFT, so that you have these finite dimensional spaces, and you can talk about these integers as dimensions of those spaces. And you can basically use an isomorphism between certain the twisted sector Hilbert space and certain Helm spaces to show that basically that F of L is the sum of algebras. Let me go to one interesting application and conclude the talk, because it's already past 1 hour. But basically, if you go through this argument, like the fact that every time you have this multiplicity, it is a dimension of the Hilbert space, and you use this isomorphism, you can show that the number of times a line operator appears in F of L is equal to the number of times a line operator appears in the sum, which is saying that these are the same as objects. So as objects or as line operators, F of L is the same as the sum, because the number of times a line appears in this can be shown to be equal to the number of times a line appears in this. So yeah, I will not spend more time on this proof. So let me quickly say one application and conclude. So what we learned is that these non-anomalous algebras can be obtained from the bulk Lagrangian algebra. So if we choose some random line operator in the boundary category, whether that line admits algebra structure, or in other words, whether that line is anomalous or not, depends on the existence of certain Lagrangian algebras of the SymTFT. In particular, if we assume that some line A is non-anomalous, then when you apply f of L to some Lagrangian algebra, that f of L should contain A, because all such A's come from applying the bulk to boundary map to some Lagrangian algebra. So if you assume that A is non-anomalous, there must exist some Lagrangian algebra whose f of L contains A. So this is a necessary condition for A to be non-anomalous, and that can be written explicitly using these numbers, these integers that appear. This integer a, b is just saying that between a and b, there should be some hom, which means that a and b should be line operators, which can form a junction. This n, l, a, comma, e, a is telling you that this bulk line operator must be in the Lagrangian algebra. So there's this particular sum of integers which must be non-zero for A to be non-anomalous. This is a necessary condition. And the thing is, when you take some random A, you will not have a Lagrangian algebra which satisfies this condition. In fact, you will not have enough bosons in the bulk SymTFT for you to satisfy this condition. That is how you can rule out and say that some lines are definitely anomalous, because this is a necessary condition which is often violated. What you can do with this condition is that you can show something specific about faces where the symmetry is preserved. When you have a trivially gapped face with some symmetry C, the existence of such a face can be transported to a statement about Lagrangian algebras. And basically what I want to show, I won't go through the argument here, but what we can show is that if you want a face where the C symmetry is completely preserved, that means that the TQFT has a unique vacuum, C symmetry is acting on it. If you want to have such a face, f of L, when you apply f of L to some Lagrangian algebra, it should contain only one copy of the identity. So this is different from like one of the Lagrangian algebras that we saw in the S3 case, where when you apply f, you get many copies of the identity. So if you want to have a face which completely preserves the category C, you should have some Lagrangian algebra such that f of L should contain one copy of the identity. Recall what f of L means. F of L means ending L, like trying to fuse L on the gap boundary. And one copy of the identity in f of L means that there is no line operator in L which can end on the canonical gap boundary. So the condition, let me quickly write down the condition, f of L must have a single identity line, means that no non-trivial line in the Lagrangian algebra can end on the canonical gap boundary, which is a statement, the nomenclature that is introduced in this paper, that L is a magnetic Lagrangian algebra with respect to BC. So this is a condition that was described in this paper, and for Tamra-Yamagami categories, this condition was very useful to determine when that category admits a trivially gap face. And you can think about this condition, the magnetic Lagrangian algebra condition, as a special case of this necessary condition when you want to have a completely trivially gapped face. So I just want to mention that as an application, and let me stop here because we are over time. Thank you.
Thank you. Thank you for the super cool talk.
Yeah, I wish I could go through some other things, but hopefully the examples were clear. So
Yeah, no, it's super. Yeah, it's super nice and clear. Yeah, and we seem to be continuing the tradition of food themed.
yeah,
Yeah.
I didn't include it in the paper, but I just wanted to mention it in the talk.
I
Yeah.
see. Tom, Roman, do either of you guys have questions? We had a lot in the middle.
Well, it was pretty clear. So,
Yes.
thank you.
Same page as Roman.
Right, I'll stop the recording.